Hello everyone. I'm going to be working through an example using an inductor, and we're going to determine its waveforms, for current, voltage, power, and energy. So we've studied the capacitor and capacitor waveforms, and we've studied the inductor. Now we're going to see how waveforms for the inductor work. Okay, so we usually have a question on either capacitor waveforms or inductor waveforms, so this is going to be good practice for you. I'm going to work out the math in great detail. So now let's imagine the scenario where we have a 2 Henry inductor, okay, and we're given a certain current flowing through it, so that's I of t. And the I of t waveform is given like this. It's some funny waveform which rises up to 3 amps, then drops down to minus 3 amps, goes steady, and then rises back up to 0. So it's a completely arbitrary waveform, and then now we're going to see what the voltage and power and energy waveforms are going to look like in this situation. Okay. So the approach we're going to take is going to be the same as what we did for the capacitor example, and we're going to divide into time intervals and do a piecewise analysis. So we're going to divide into this time interval and examine this current, and then we're going to go and do the second time interval and examine this current. Okay? Then we're going to do the third time interval and this current, and then finally the last one. Okay, so that's the approach we're going to take. Now let's start our analysis. So I've redrawn that current waveform, so that's given to us by the problem statement, and what we're going to do is we're going to find v of t, and so we're going to just plot it down here. Okay, and so I've also shown the plots for P of t and energy. We're going to be working on that later. Okay, so let's get started with finding V of t, the voltage across that inductor. Okay, so the equation that we're going to consider, right, is going to be voltage is equal to L di dt. Okay, so this is a really important equation, and it relates the voltage to the current. Okay, so now how do we start this? How do we get our information? So we need to find di dt, but let's take one step back and find I of t. Okay, now it's looking at this plot, it's very easy just to find di dt directly. Okay, but when later we're going to do power, we're going to multiply the current and voltage waveform. So I'm just going to go ahead and solve for the I of t lines, and then find our voltage. Okay, so that's what I'm going to do. So first, let's find what our di dt is. Okay, so what we're doing here is we're doing rise over run, just like in high school or whenever you started learning about graphs. Okay, so the top here, it's the rise. Okay, so it's starting at 0 and then ending at 3 amps, so that's what we have there. And in terms of time, it's starting at 0 and ending up at 0.1, so that's the run. Okay, and that so that should be very familiar to you, and then that works out to a value of 30. Okay, I've put the units in here, but that's just to be kind of complete. Okay, but the value is 30, the slope is 30, and di dt is the slope. So we can write I of t in the form of an equation of 30t. Okay, and the slope, of course, coming in here. And then, so then we can label that part of the graph as I of t is equal to 30t. Okay? So then let's find the voltage. So the voltage, we know, is equal to the inductance times di dt. So remember, our inductor was a 2 Henry inductor. That's what we started with on the first slide. Okay, it's a 2 Henry inductor, and we found our di dt was 30. Okay, and that works out to 60 volts. Okay, 20 times 30 is 60. So then that's a constant. So we're going to see a constant line for the voltage, okay, with a value of 60. And here I've labeled that segment as V of t is equal to 60. Okay. Straightforward so far, right? Okay. Let us do the second time interval, okay? So that's going to be the voltage in this time interval. Oh, sorry, it's even further than that. It's this time interval, okay? So now, what's di dt? So this is the rise, okay? So we're starting off at 3 amps and ending off at minus 3 amps. So that's what we have on the top. And on the bottom, we're going from 0.1 seconds to 0.3 seconds, okay? So that's what we got on the bottom. And that works out to minus 30, okay? Minus 30. So then, what's our equation for I of t look like? So, we drop down this is the slope, okay? So that's where we get the minus 30t from. But, you know, we know that we have some sort of y-intercept, okay? We know this line's going to eventually hit somewhere, okay? So we know that there's a y-intercept. So we're just labeling that as a k plus k, some k. So now how are we going to solve for this? Okay, how are we going to solve for the k? Well, we know a data point. We know this data point here. That's where that line becomes 0. So that line becomes 0 at 0.2 seconds. So I of 0.2 seconds is 0, okay? And that's equal to that equation that we found at 0.2 seconds, okay? And now we can solve for k very easily, and k is equal to 6. Okay, so now let's plunk that into our equation. So I of t is equal to minus 30t plus 6, okay? And we've labeled that here, okay? That's nice, okay? And then we can calculate the voltage, okay? So then the voltage is L di dt. So our inductance is still 2, and our slope, minus 30, comes down here, okay? And that works out to minus 60 volts, okay? So V of t is equal to minus 60 volts for that interval, okay? For that piece. So that's labeled down here, okay? So that's this line right here. Okay? Okay, straightforward so far? Okay, let's do the next one. Next one is this interval here, okay? So that's 0.3 to 4 seconds. Okay, so now here we know that I of t is equal to 3. We don't need to find the slope. We know di dt is equal to 0 because it's a horizontal line, okay? It's a constant, and the derivative of a constant is 0, okay? So then, when we do our voltage, L di dt, still 2 henries, but our di dt is 0, so we get 0 volts, okay? And that's what we've labeled here. So the line actually is right on the horizontal axis, okay? So it's at 0. Okay, that's good. That one was easy. Okay, let's do the last one. So we're doing the last time interval, and that's this time interval here, and we want to find the voltage. And so now we're going to go back to our rise over run. So we're starting off, oops, what did I do there? So we started off at minus 3, okay, so that's this. And we're going to 0, so that's this, minus 0. And then we're going from 0.4 seconds to 0.5 seconds, which is expressed here. So we have 30 as di dt. Okay, let's plug in. We know the routine now. We're going to have some I of t being equal to 30. So this 30 comes down here. It's 30t. 30 is the slope. And we know we have some sort of y-intercept, right? You know, that y-intercept is shooting down that way, right? It's going to be some big negative number. So then we know a data point, don't we? We know a data point. We know the data point of this one right here. At 0.5 seconds, that graph is equal to 0. Okay, so when we plug in 0.5 into the equation, you know it's going to be equal to 0. We can solve for the constant for the y-intercept as minus 15. Okay, so then we can just plug that in, and then we have our line. So I of t is 30t minus 15. Okay, and that's labeled right up here. Okay, so that line segment is right here. Okay. Okay, and then when we do the voltage, V is equal to L di dt, 2 henries times 30, which is di dt, works out to 60 volts, okay? And that's a constant, and that appears right up here, okay? And that represents that line segment right up there, okay? So that's how we do the voltage. We found the voltage. So then, let's find the power. Okay, so when we're solving for the power, we use the relationship P is equal to V times I. Okay, just like for the capacitor, just like for the resistor. Okay, so let's consider our first time segment, or time interval, 0 to 0.1. Okay, what's the power? So power is voltage. So the voltage is here, right? It's that line, and that's the function, okay? It's voltage. V is equal to, Vt is equal to 60, V of t, and that's what we have here. That's 60, okay? And then we need to multiply by the current, and the current is this one in that first segment, represented by that line there, and this is what that 30t is representing, okay? So that's where we get that from, and we just multiply them together. So that works out to 1800 t. P of t is 1800 t. Okay, so that's a line that's going up like that, a nice simple line. Labeled it as P of t is equal to 1800 t. Okay, so now let's see how high that line goes up. So then, you know, the line terminates at 0.1. So then let's plug in 0.1 for t and calculate, and then we get 1800 watts, okay? So then we can put 1800 watts there to label the top of that line, okay? So that's right up here, okay? So straightforward. Okay, so now let's do the second time interval. So this is the time interval that we're doing for power, and I've already drawn the line, but let's work out the math. So looking at the power here, it's voltage, so minus 60, so the minus 60 is coming from here, okay, times the current, which is this one, minus 30t plus 6, and that's coming from here, okay? So that's this segment times this segment, okay? Those two line segments for current and voltage. So then when we work that out, we're going to get P of t being equal to 1800 t minus 360, okay? And let's do the boundaries of that line on each end. So we had started at 0.1, okay? P of 0.1 is minus 180 watts. So that's this end right here, and we have 100 minus 180 watts here, okay? And then at the other end, at 0.3, P of 0.3 works out to 180 watts. So it actually climbs up to the same point as this one, okay? So that's that line, represented by that function. It's labeled P of t is equal to 1800 t minus 360, okay? So let's do the last interval. Oh no, the third interval. So that's this interval right here, okay? And this one's an easy one to do because the voltage is 0. Right here, the voltage is 0, and it's multiplied by the current, which is minus 3, which is over here, this line segment here. So that is going to equal 0. So the power is 0, so it's labeled as P of t is equal to 0. Okay? Now let's do the last time interval. So the last time interval is this one. Okay? So then P of t is equal to 60. So remember, it's V times I, right? So it's 60. So this is 60 volts representing this time interval. And then multiply it by this 30t minus 15, which is the current and represented by that function, okay? So that's why we went and did the I of t's for the current so that we could use it for the power, okay? So then that works out to 1800 t minus 900, okay? So then we can put in the data points. So at 0.4, it's at minus 180. So that's this point down here. It's minus 180, same as the other one. And it rises up at time 0.5 to 0. Okay? So it rises up here. So that's a line segment, and this is just writing the equation for that line segment for power right there, 1800 t minus 900. Okay? So now, so that is the power. Okay? So I hope that makes sense. There's a lot of fairly simple algebra and graphing, and what we're doing here is getting explicit expressions for the power. Okay? So it's all mathematically based, and when you do the exams, we may ask you to write the equations. Okay? Sometimes you can just do this graphically and visually, but you have to do it with the more mathematical, more rigorous way that I've done it, so that you can get specific numbers for the line segments, or specific functions for the line segments that we've drawn here. Okay. So let's go on to energy. So energy, we're going to use 1/2 Li squared. Okay, so that's a really important formula. So we're going to use that one. Okay. Now remember, when we did the capacitor, we also did it with the integral of power. Okay. So I'm not going to do that in this example. I'm going to use 1/2 Li squared. Remember, in the capacitor, I did 1/2 CV squared, okay, and then I did the integral formula for power. So I'm skipping the integral formula. Okay, so now let's consider the first time segment here, okay? 0 to 0.1 seconds. So then we have the equation for energy is 1/2 Li squared, and that's equal to 1/2 here, and then 2, because we have a 2 Henry inductor, right? That's what we're working with. And then I, this is I, so 30t is I, and of course that's coming from up here, okay? So we're using the mathematical form again, right? So it was good that we found the functional representation for those line segments in the beginning. And now, don't forget, we've got to square this, okay? We've got to square that, okay? So then, that works out to 900 t squared. And let's get a data point for the end of the interval, right? So at 0.1, it becomes equal to 9. And the line is drawn here. You know, it's a quadratic. It's very straightforward. And it rises up to 9, okay? 9 joules. Okay. let's do the next time interval. So we're doing this time interval here, okay? And then, so it's 1/2 Li squared. So that's 1/2 L, which is 2 henries, and this is the current in here, minus 30t plus 6. So that's the current right here, right? So that's this segment right here, this line segment, okay? And then when we work out that square, we get 900t squared minus 360t plus 36, okay? So that's some quadratic. Let's get the points on either end. So at the beginning of the interval, at 0.1, we get 9 joules, which is good because we're starting off where we left off, right? We're starting off right here. And then right in the middle at 0.2, we get 0 joules, okay? So it's going to come down, and then at 0.3 at the end, it's going to go back up to 9 joules. So it's going to go up like that. So let's draw that, and it's in the right places, and then let's do the next time interval, okay? So we're doing the time interval here. So power was 0, what's going to happen, okay? Let's work it out. So energy is 1/2 L I squared, right? I is minus 3, okay? I is minus 3 in that line segment. We square it, and we get 9, okay? That's a constant. So over here, it's going to be a constant at 9. So that's the line segment. It's a constant at 9. So then, let's do the last time interval. Okay, so we're doing this one here. So it's 1/2 L I squared, okay? So then that's this line segment represented by this equation, and then when we work that out, so don't forget the square on it, when we work that out, it's 900t squared minus 900t plus 225, okay? And let's get a couple data points. At 0.4, it's equal to 9, which is what we want because that's where we left off with the previous line segment. And then at the ending, at 0.5, the energy is 0. So it's going to come back down to 0. Okay? And that's what it looks like. And then finally, let's just label all of those line segments as shown here. Okay? And that is a complete worked solution with every line segment described by its mathematical equation. Okay? So you may expect to see a problem like this on the exam. Okay? And remember, in this problem, right, you were given I of t, right? So you were given this line, right? However, you know, think about that you might be given v of t, and you might be given the plot of this, right? And then you would have to get I of t and develop it, okay? And then from that, do the power and energy waveforms, okay? So you'll have to use the relationships that you know to go back and forth, okay? Okay, that's it.